Okay, I think we'll go ahead and get started, and we'll hope that technology works with me again this time. So welcome to a talk on EEG with and without simultaneous fMRI. This is the second talk that I've given in as many days. So for anyone who wasn't here last time, last week I talked about multimodal neuroimaging, mostly in a high-level forest theoretical sense on pros and cons of doing multimodal. Today is going to be a lot more focused on EEG, although there may be some overlaps. So if you didn't see the talk last time, you can now stream that. Okay, so I got my start in EEG at an early age. This is me at, I think, 17 months on my mom's lap. You can't really see the electrodes on my head, but they are there. This was with 6 channels of EEG. My dad's taking the photo, and also he was the one that put the electrodes on me. And then if we fast forward somewhat to when I was an assistant professor, this is me now with 256 electrodes with a former graduate student putting them on my head and then triangulating all of the electrodes on my head. So nature and nurture is certainly a thing. It's hard to tell where this desire to continue doing EEG in my parents' footsteps came from, but it's there. And just in time, because much like EEG, I'm turning 100 this year. EEG was first discovered by Hans Berger in 1924. For a little bit of background, Hans Berger lived from the late 1800s to the mid 1900s. He was a physician, lecturer, and chief of medicine, and he discovered EEG at first in 1924 doing a eyes open, eyes closed experiment and just measuring the amount of alpha waves and beta waves. The paper was published in 1929, and it was not well received. There was a lot of controversy about, can you actually measure what's going on in the head, and does the brain even matter? Because dualism was still a thing. But his findings were later replicated in London in 1934, and that seemed to make things considerably better. Shown here, kind of an early EEG device, participants' foot in bucket with single electrode. And then we progressed in the 80s and early 90s into sort of EEG equipment that would take up an entire room for doing 4 to 8 channels of electrode recording. And then sort of the grass instrumentation cart of, I think this is a 16 or 32 channel EEG cart that you could then wheel from room to room to do recordings. And importantly, all of these probably cost about the same with inflation calculated in. I showed this last time and can't see my mouse, so sorry that my mouse doesn't show. I'll just gesture widely from here and the camera will have to pick it up. So EEG and MEG, you can see here in the upper left-hand corner, have great temporal resolution and sort of okay spatial resolution. So the spatial resolution is going down to, say, millimeters or centimeters while you're doing source analysis. But in terms of temporal, we can sample at several thousand times a second. Some of the amplifiers that we have here actually can go up to 40,000 hertz. So 40,000 samples a second. Coincidentally, a lot of people who collect that quickly end up downsampling later. And as I talked about last time, EEG is great because you can put it together with some of these other techniques like fMRI for getting better spatial resolution at the cost of those techniques having slower temporal resolution. EEG is a pretty straightforward method. So you have sort of dipoles in the head, which are synchronized electrical activity from large groups of neurons, mostly pyramid cells. And they fire together. And then from there, you get sort of a distribution of electrical currents across the head, shown here in the bottom left. We measure those electrical currents across the head with electrodes, with either lots of electrodes or very few electrodes. And then those are amplified by an amplifier thousands of times, and then we can record them on a computer as little wavy lines. No one seems terribly confused on this. It was simple back then, it's simple today, but we've managed to make controversy out of just about everything else. EEG reflects a number of different brain states. I'm proud that all of them are being represented in this room right now. So you can tell if someone's excited, relaxed, drowsy, asleep, or even in deep sleep. This is almost as good as having an eye tracker on someone inside the scanner. And then within all of these sort of collective EEG waves, if you were just looking at that, you can actually decompose all of the EEG into different frequencies. And so they're here on the left, so delta, theta, alpha, beta, and gamma. And some people now make a distinction between low gamma and high gamma. And actually this figure here on the right is from a book that I have been reading on speech perception and emotional recognition. And they kind of take a stab at what some of these different frequencies pick up on, although it's somewhat limited. So for instance, they say that theta is associated with drowsiness, but you know, any kind of quick search will pull up dozens of other things that theta is implicated in, whether it's attentional control, whether it's arousal, which I guess could be related to drowsiness, emotional processing. And it's also been used, theta in particular has been used to study things like major depressive disorder, and also just how good you are at perceiving different things, like just noticeable differences in sound and vision. If you are interested in learning more on the EEG side of things, like how these frequency bands can be used to study your favorite clinical disorder, I highly recommend these two books, particularly this one on the left by Paul Nunez, Electrical Fields in the Brain. A kind of incredible collection on all of the ways that people have measured these frequencies and then sort of made insights into how the brain works at kind of rest. Most of what I am going to talk about today, though, is the event-related potential. So this is time-locked EEG. And so if you can imagine, well, you don't even have to imagine because there's a figure here. We have this ongoing EEG here at the top. And every time you see an S, maybe we're playing a sound. So you hear a beep every time you see an S. And then if we take all of those times that you heard a sound and we average them together, we get this, in this case, auditory evoked potential. This is called the ERP, as I just said. Never ERP. Just kind of squash that while we can. It is a portion of the ongoing EEG that is time locked to some kind of stimulus onset. That stimulus onset could be any number of things. It could be visual, it could be auditory, it could be somatosensory. I have seen smell, taste, touch, even like perceived touch, even people who sort of use their own internal timing. It can be reaction time based. So when they push the button, you can get an ERP following the push of a button. And I'll talk about that a little bit later, particularly if they know, or even if they don't know that they got the answer wrong, they'll get an ERP to that. ERPs, of course, have strong temporal information, so we can break down what sort of each of these peaks means. And they're very comparable across the lifespan. Manny Adamson, who could be referred to as the father of modern EEG and ERPs, has this quote that ERPs are a sequence of overlapping components, each perhaps representing activity of different populations of nerve cells, and each sometimes standing in different, sometimes perhaps orthogonal relation to experimental variables. There's a lot of hemming and hawing there, but essentially ERPs with all of these peaks and valleys are thought to be sort of separate parts of the brain coming online and integrating different information. And as I'll show you later, that's pretty true. What? Yeah.
What was the dotted line?
Oh, I'm going to get to that later. Don't read it. Yep. What I like about ERPs in particular is that they're very comparable across the lifespan. So you can put an infant in an EEG cap, you can put an adult in the same EEG cap, and you can get kind of similar information. So ERPs have been used to predict all sorts of behavior and clinical conditions. For instance, we can predict your reading ability and your chance of having dyslexia when you were 1 day old, with about a 96% accuracy in that prediction. Can do similar things with autism and then other clinical disorders. And then shown here on the right is sort of the ERP over these first few years of age. And as you'll notice, the ERP in your first few years starts to get larger and faster. And then once you hit about 7 or 8, the ERP starts to get smaller again and even faster. So basically, your brain is better responding for a while. And then, of course, your skull gets thicker and you get more efficient at doing things. I really like showing this movie. So this is a infant EEG recording that we did in one of the hospitals in Louisville, Kentucky. So this baby is less than a day old, kind of go in, obviously, with parent permission into the nurseries. And first thing we do is we say hi. They're pretty happy to see us. Then we measure the head. So we get the head circumference to identify what size net that we're going to put on the infant. The next thing is we make a couple of measurements for finding the center of the head, nasien to enyen, and then meatus to meatus for ears. The net itself, in this case, has been soaking in a saline or potassium chloride and baby shampoo solution to break up oils on the scalp and also conduct electrical activity. And then sneak up behind the baby, and it goes on in one nice fail swoop. Sometimes they wake up, sometimes they don't. Generally, they're pretty content. So this actually has 128 electrodes in it. And then next thing is we lay the baby down. We'll measure the impedances, which are the resistance between each electrode and the electrical current naturally happening across the scalp. And then we'll play some speech sounds in this case to predict later language ability. And then the net comes off, dry off the baby's head, sometimes change the diaper, and then rush off to the next one before they get discharged from the hospital so that we can collect as many as we can. At sort of our peak, we were collecting about 12 babies a day at the hospital, which given that babies are only in the nursery for like 1 to 2 days, that is a pretty quick clip, but not fast enough to really keep up. ERPs have a number of really cool and obvious measures. So the first thing is that we have amplitude and latency. So for this large peak happening at, say, 100 milliseconds, we can say, okay, it happened at maybe 104 milliseconds, and it was negative 18 microvolts. But in addition to this, keep in mind that we have lots of sensors over the entire head. So we also have scalp topography maps that look like this. And so for every time point, not just these 4 time points, but clearly if I'm sampling at 10,000 hertz, for all 10,000 time points over that second, I have a map that looks like this in the upper right corner. And that means that I have differential spatial information for every electrode. I also have this changing over time. So I'm going to show you 2 movies. The first one is going to be an infant brain responding to the sweet sound bop, and looks like this. Nose is up, left is left, right is right. So you can see there's some initial positivity that happens sort of here in the frontal central region, just kind of hangs out there for a while and then goes away, and then we get a positivity sort of the left posterior bridal regions. That kind of hangs out for a little bit and then goes away. Now I'm going to compare that for you to an adult hearing the same sweet sound and just note the difference. So for an adult brain, you can see that the activity is both faster and more dynamic, more integrated. So we aren't seeing discrete presentations of positivity. We are really just seeing voltage being pushed around from place to place. And at this point, they're probably thinking of their grocery list or what they're going to do with the $50 that we paid them for this particular study, and a number of other things. Everyone saw those differences? Yeah, I see a lot of like early drowsy EEG. All right, coming back to Tyler's question, what is that dashed line? So this is the ERP, and I'll just take a moment and talk about ERP nomenclature, which is that we like to name peaks based on the polarity, positive or negative, and then either the ordinal number, like first peak, second peak, third peak. So P1, N1, as in the first positive peak, the first negative peak, or the milliseconds that that peak happened roughly. So P50, N100, N200, P200, and these shift depending on where on the head you were measuring. The peaks that happen before the dashed line are identified as being exogenous peaks. So they're driven mostly by the characteristics of the stimuli. So if you have a sound, you get an N100. If you play a louder sound, you get a larger N100. There's a nice direct relationship between how loud the sound is in the N100 or how bright the image is in the N100. Shows up very clearly. The endogenous peaks are thought to be internal processing, and we know that to be true because, say, if you have a P300, which is way after you would notice that two sounds have a different sound, you're playing sort of a repetitive sound like ba, 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 and I throw in a da, you get a P300 to that infrequent target stimulus. So your brain is able to pick up on that very quickly. There have also been studies that have shown that you can pick up on that even if the stimuli are being rapidly presented. And I'll talk about that a little bit more. This is sort of a classic figure in terms of like, this is what, you know, if I was going to draw, in fact, my dad drew this figure of sort of the idealized ERP. This is what it would be, and we would kind of highlight the most major peaks. If we were going to measure the sort of peak amplitude and latency, this is actually an old program, literally written by my dad, and I used in my early PhD days, written in future basic of all things. We have a number of different measures that we can use. So is the peak positive or negative? What is the latency of that peak? And is that peak represented similarly across all of the electrodes on the head? And oftentimes that's not the case. So every time that you go over a sort of a sulcus or a gyri, you will see a flip of polarity. And so sometimes in one place you'll have a N1, other places you'll have a P1. And so oftentimes early programs for measuring peak amplitude and latency would try to get you to fit things between two bars and then separate them into parts of the head depending on whether it was positive or negative. Many of these peaks have been studied, I would say ad nauseum, but like they're still really interesting because everyone finds new things about them. There is a paper that's referenced here in the upper right corner by Sasha Key. Mandy McGuire is the senior author on it, published way back in 2005, I think. And it kind of breaks down the name of the peak, the latency of the peak, the experimental manipulation that you are most likely to see that peak, including where you're going to see it both auditory and visually, and then sort of an interpretation of that peak. And in some cases, we know generally the sources that have generated those peaks. So for instance, the P100 is a little bit faster in auditory processing. The auditory system is a little bit older than the visual system, so a little bit more efficient. So the P1 happens at about 50 milliseconds in auditory and 100 milliseconds in visual. It is anterior for auditory because basically auditory cortex happens. There it goes. Screen's back. Auditory cortex kind of points up and forward. It's going to be really interesting for you all if the screen doesn't behave. Whereas visual obviously is happening over occipital cortex. I'm not going to step through each and every one of these because I have several pages of these, but this is just to give you a sense that these peaks are incredibly well studied. And in many cases, we know how to evoke them. And the interesting part then becomes, how can we manipulate these peaks based on characteristics of our stimuli, characteristics of our participants, or any number of combinations of that. So do you have a different N100 between a clinical sample and a experiment or a control sample? I want to highlight one ERP component on the second slide, which is the P3 or the P300. It was originally discovered by Sam Sutton in 1965. It is often seen as one of the most famous peaks. This is what pops up if you were playing sort of a repeated tone and then you have a outlier or oddball tone, so to speak. The P3 is incredibly reliable, so reliable that the joke is that anyone who's going up for tenure immediately starts running a whole bunch of P300 experiments, because you can take a P300 and be like, I know the P300 is going to be there, just how can I manipulate it based on stimulus characteristics or population characteristics? Other famous components shown here, the N400, first discovered by Marta Kutas and Steve Hilliard in 1980 for sort of like squiggly sentences that have congruent or incongruent endings. So if you're listening to a sentence and you're like, yeah, this totally makes sense. And then you're like, you know, the horse jumped over the fence, like that makes perfect sense. But then you might be like, the horse jumped over the barn. Barn's kind of an unexpected thing, even though it's a related semantic category. People might be like, wow, that's a really big horse, a really small barn. But you'll still see this N400 effect come up. And then I sort of hinted or alluded earlier to two peaks that are related to responses. So the ERM is the air-related negativity, first discovered in 1990 by two different groups. And the reason why it was sort of two different groups, one in 91 and one in 93, is that they named them slightly different things. And it took a while before people realized they were the same thing. So in 91, Michael Foxstein called it the air negativity. And then in 93, William Gehring came up with the air-related negativity, which is the name that kind of stuck. And this pops up anytime that you are responding to a task and you make a mistake. And it doesn't necessarily mean that you know that you made a mistake. That's not required. Your brain knows that you made a mistake, which is kind of cool. This does, I see lots of people being like, does this scale to narcissism? Yes, this scales to narcissism. Now I just have to wiggle my mouse every so often. Also, the feedback-related negativity, also by William Gehring, was discovered in 2002. So this is when you're doing a task and they present you with feedback and say, you got it correct or you got it incorrect. And this is particularly cool because this scales with how much you believe in that feedback. So do you think, given the response, like, yeah, I totally got that wrong? Big FRN. Are you in denial of that FRN? Small FRN. People with higher anxiety show larger feedback-related negativities than people with lower anxiety. All sorts of gambling tasks have been centered around these two components in particular. And then the CNV, shown here last, is the contingent negative variation. So this is right before we have all of these peaks. You have the time before, and if you are anticipating a particular thing to pop on the screen, doesn't matter what that thing is, you're just like in anticipation, the EEG kind of goes negative right beforehand, and it goes more negative depending on how anxious you are, how excited you are, a number of other traits. And this is why we always jitter our experiments so that we have a little bit of variability so you can't know exactly when the stimulus is going to come on. Of course, measuring peaks gets burdensome and tiresome because it means that you have to measure them by hand or like maybe even an automated software, but then you might have to set parameters and then those might have to be like replicated by another person in the lab. And we have done studies on like how well two people will characterize the same peaks, and it's okay, but you know, we're talking about correlations of like 0.5, 0.6. In contrast, we have multivariate alternatives to analyzing data. So principal components analysis is known for a lot of things, but we can use it for ERPs. So if I put my ERP into a PCA, I can do either a temporal PCA, a spatial PCA, or both, just depending on like which columns are time and which columns are, and which rows are, what in that case, channels, or I can flip it and make my variables channels and my cases time. So in this case, we tend to do a sort of two-factor PCA. So we start with a temporal PCA, and we get this figure here in the upper left corner. And what this shows us is where those components are in time. So each PCA comes a latent variable, and those latent variables are most active. Granted, they're active over the entire decomposition, but they're most active with the highest loadings at different times. I can then submit those to a spatial PCA, and then I get sort of this combination where each row in this case is a temporal PCA component, and then within it, I get a bunch of spatial PCA maps. This is particularly handy because then you can do things like bootstrap ANOVAs, and you can test your differences between conditions, between participants, based on the temporal spatial time points, both in time and then also the electrodes on the head. And it looks something like this. So just pulling out one set of temporal spatial components. This is a sleep restriction study with astronauts funded by NASA originally. And it corresponds to, say, this temporal component and this spatial component. And so you can even see that the electrodes are centered in sort of that large blue negativity in the center of the head. And lo and behold, if I do a bootstrap ANOVA over those three conditions for the mean amplitude of those conditions, I find a significant effect. What's great about PCA is that if I run it, if Tyler runs it, if Fernando runs it, we're going to get the same thing as long as we agree to the parameters beforehand, and it's not going to be judgmental. It used to be that PCA took you a long time to run because you had a calculator with a memory of one and a pad of paper. But even in the 90s, and for that matter, 80s, you could run a PCA in a couple of seconds. Even on large data sets like this, which was a couple hundred people, this PCA runs in under 5 minutes in both the temporal spatial in MATLAB on my Mac. PCA is certainly not new and not new for EEG and ERP experiments. Manny Danchin mentioned before was doing this in the 80s. My dad did it with PCA feeding into the ANOVA originally, sort of 70s, 80s, and then really they became sort of more, yeah, just to be clear, that's not me. I was alive in the 80s, but barely. Really, these became a lot more tenable with the introduction of toolboxes like this ERP PCA toolkit by Joe Dean. And Joe's a researcher at the University of Maryland now. He started off as an assistant professor at Kansas. And just to give you a sense for how many people use this or use this technique, just a quick Google Scholar shows that just the PCA toolkit has been referenced 600 times. And as we know from anyone who uses AFNI, FSL, or SPM, people don't always reference the toolboxes that they use for analyzing their data. So likely many more publications are generated from this. So peak picking is fun, but PCA is better. I will give some caveats to peaks. So peaks are peaks, but are they really peaks? Try saying that 10 times fast. ERP peaks, remember these are averages. So a lot of things can influence how pointy your peaks are. So if you have more variation in your trials, then you'll get sort of smaller peaks. And sometimes shown here on the left, there's a bimodal distribution to the peak. Whereas if you have less variation, you'll get a pointier peak that will be larger. And also the number of trials that you average together will influence how big or small your peaks are. And so it's important to come up with some way of regularizing or normalizing your peak size. You can do this both in just like selecting the number of averages from each condition. Say like, I'm only going to take 25 averages from each condition, even if I have 75 trials in one and 30 in the other. But you can also do it in PCAs by, instead of using a covariance matrix, you can use a correlation matrix, which will kind of normalize your peaks over time. We do know that there's sort of a relation of trials to signal noise, and generally the equation is that your signal noise ratio in ERPs is 1 divided by the square root of n. So if you have 25 trials, then 1/5 of your signal, or 1/5 of what you're recording is noise. There's kind of a nice handy-dandy charts published in '92 for kind of the trade-off for the number of trials. And you might be like, okay, well, you know, that's a lot of electrodes, that's a lot of math, even if I don't have to look at the math. Do I really need high sampling rates and lots of electrodes? Well, it turns out, yeah. I generally, even though I said last time more data isn't always better, I generally advocate for more data is usually better. And so in EEG and really any temporal sampling, there's this thing called the temporal Nyquist, which essentially comes down to if you are sampling really quickly, you get the true shape of whatever waveforms that you're trying to sample, getting closer and closer to the true signal. But if you sample, say, only every 10 or 15 data points, you may be missing out and you may end up with sort of this very smooth curve here on the bottom left. And then if you look at the frequencies that are represented in those different EEG patterns, you'll notice that going from sort of the true signal in the top left to the bottom right, you end up seeing that your signal frequencies are also getting sampled down to slower frequencies. So you're losing a lot of information and you're attributing the signals that you are getting to perhaps the wrong frequency band. So instead of measuring gamma, maybe you're measuring theta, and you might be like, my difference is in theta, and then you'll present your work at a conference and someone will come up to you and be like, sample faster. And you'll be like, oh, okay, that's why I'm out of step. In addition to the temporal Nyquist, there's also this spatial Nyquist. So here is a map of the top of the head, and so you can see what it would look like if we had a different number of channels on top of the head in terms of the true signal on the bottom and then sort of the interpolated signal on the top. And as you can see, more sensors allows you to pick up on what the topography or topology of this will actually look like. That wasn't already enough information. I am not legally required, but strongly encouraged to talk briefly about time frequency analysis, which is wavelets and FFTs. Bear with me. So in addition to peaks and head scalp topographies, we can also just sort of describe our EEG and ERPs as time frequency analyses, which are sort of when in time. In this case, this is a wavelet shown here on the left. So on the x-axis, we have time from 0 to 1 second. And on the y-axis, we have different power bands. And then anytime that you see a burst of color, that is how intense the sort of power is in that frequency band at that time. So wavelets, FFTs, really here we're just trying to measure the oscillatory dynamics. Some people will call them spectral content. And importantly, FFTs and wavelets have shown very useful in describing different clinical disorders. So it's not just that all of your information is in peaks and topographies, a lot of it turns out to be in frequency and power. Here, all we're doing is taking our little squiggly lines and we're transforming them from the time domain to the frequency domain, but wavelets allow us to kind of have both. And wavelets are pretty similar to a windowed FFT. So if you're on a fast Fourier transform on windows of your data, you'll get something pretty close to a wavelet. You can tune them as much as you want. This is actually an evoked FFT or an evoked wavelet shown right here, which means that I ran it on a averaged ERP, but you can also get induced wavelets and FFTs based on your non-time locked or non-average data. And if you were like, wow, that's a lot of things to take in, keep in mind that you also have this for every single channel that's on the head. So if I have 128 channels, I have 128 of these. There's also a PCA for that. Yep. Just like the iPhone, there's a PCA for everything. Okay. So I know a lot of people are like, okay, like, it's cool, there's squiggly lines, they mean things. Sure, you can predict behavior in clinical disorders, and that's great, but just show me some brains, man. And yeah, admittedly, I think a lot of source analysis came about because people at conferences were like drawn to these beautiful brain images from fMRI, and the EEG and ERP people were like, man, no one likes my squiggly lines anymore. And so source analysis has really been refined. It sort of became more refined as we added more electrodes. And we have a number of best practices for doing source analysis, all of which are available here, and I will get to how to do EEG and ERP studies here at the NIH. But in terms of best practices, number one, you have to have an adequate number of sensors. What is adequate? I can't really answer that. I'll tell you, we have 256 channels. 256 channels goes a long way to getting you pretty good source analysis. You also have to know the geometry of the head and the sensors, have a head model of some kind of conductivity model, and then choose some kind of inverse model. So I think I've convinced you on adequate number of sensors. I could convince you more by saying like the time to put on 8 sensors is about the same as to put on 256 channels, depending on if you're using a high impedance system like we have with sponges that just go on like a shower cap. I'll show you that in a minute, versus a low impedance, low channel system. These all fit into a head model. So just to walk you through what that looks like, we have what's called a Ford solution. So this is the EEG sensors and their geometry. So essentially we need some way of triangulating where the sensors are on the head. We can do that using a number of different techniques. One is to use, say, like an infrared scanner, and that looks like this. So in this case, like all of the sensors have little reflective discs on them. And so as you wave this infrared camera over someone's head, you can see in the computer in the background, it is identifying where the electrodes are. You can do this in the span of a few minutes, as long as you don't show the scanner of fear. As soon as you show the scanner of fear, this will take like 20 minutes. But yes, very, very quickly. You can also do this with a number of electrode triangulation systems. So from before, this is me setting in a geodesic dome. And this has 12 cameras that all take photos of me wearing the net. And then we can use machine learning to basically place the discs, all over the head where those sensors are. And then I can build a 3D model. And of course, we can also go back to Polina style pen registration. So if anyone's done any TMS or MEG where you want to triangulate where those sensors are, you can use this little pen. There's a little button on the end of the pen, just like a regular pen, and you put it on the head wherever you want, and you click the button, and it in 3D space records where that pen is at that time. It also has a continuous draw mode, so if you just want to know the shape of your friend's head, you can just turn it on and you can scribble on their head for a while, and you can use that to sort of build a shell to say, like, this is what your head shape looks like. But if you have an MRI, you already have that information. So, knowing where the sensors are is most of the way there. I know, everyone thought, man, source analysis, there can't be any problems with this. Okay, so there are two problems that we have to solve here. The first is the forward problem. So if we are given the sources in the brain, if I tell you like, hey, I'm going to activate your hippocampus with this, or your amygdala, and only that, nothing else, and I know the propagation model of your head, I can tell you pretty much what your scalp topography is going to look like. And it's kind of, well, this isn't hippocampus, but this is going to be like sort of right auditory cortex. But anyways, I have a dipole on the head, I have a propagation model, and I can show you what the scalp topography looks like. And I can show you what that scalp topography looks like with and without noise. So I can give you a pure signal versus like a noise signal. And for anyone interested, I'm sorry that's cut off from the classroom. This is part of the BISA simulator. It's a free download from bisa.de. It's awesome. It's so much fun to play with. If you've ever been like, hey, I wonder what happens if like these parts of my brain are activated all at the same time, you can see how all these sources with different strengths culminate together to give you very complex scalp topographies. Super fun to play with. BISA also makes a lot of high-end software that we also own that allows you to reverse this with real data. The second problem after the forward problem is the impossible one, right? So this is the inverse problem. This is given a scalp topography and propagation model, what are the generators of that current? And this is impossible because there's so many neurons in the head. There's so many ways that this could go together. And I will say, like, I know sometimes that sounds like doom and gloom, but you could look at this as saying like, okay, I'm gonna take a thunderstorm and I'm going to say, I want to predict where lightning is going to strike next. And I can do that as long as I put enough mathematical constraints on the model and say, lightning is going to strike here next. I do that with EEG too. And that's what makes source analysis canonical. So a sort of propagation model, this is a boundary element model shown here, and a brain seeded with all the possible dipoles that I'm going to allow to be active in my experiment. These combine to give me sort of a propagation model that allows us to then solve the inverse problem. The forward solution, yeah.
I noticed that there were no nodes on the cerebellum. Is that common practice to not include?
Different softwares allow you to segment the cerebellum and others don't. This is a free server based segmentation. Yeah, I can give you the people the email that keep saying cerebellums in the next version. I just want to break down briefly the difference between FEM and BEM models. I don't expect that anyone's going to be like, oh man, it's not like you walked into a car dealer and you're like, a Subaru instead of a Porsche. Like, these are both really good head models, and they've iterated quite a bit. So the first is the BEM, the boundary element model. This uses, I put simple in here, but honestly, simple is doing a lot of lifting here. It's a simple, air quotes, 3-layer model. We're modeling the scalp, skull, and the brain, and it's called a boundary element model because it's really looking at how the separation between those interacts. This all has isotropic conductivity. So conductivity is going to be the same within each of those. BM model, or someone said here. Finite element models, in contrast, are a little bit more complicated, but not a huge amount more complicated. So at the very basic level, finite element models also model the CSF. But beyond that, they are also going to break down the brain into very small elements, either tetrahedrals or hexahedrals, each with specific conductivity properties. And what's really cool about FEMs is that these can be not symmetric. So you can say it projects in this way with this type of current flow, and it goes the other way in a different way. So FEMs are super cool. They're available. Both of these are available in a lot of different softwares. BEMs are kind of the FreeSurfer M&E Python sets. FEMs are available in FieldStorm or FieldTrip and Brainstorm. Wow, just mush those together. Or possibly a great collaboration, guys. Yeah. Oh, yeah. And here's sort of the FEM shown next to the BEM in the upper right corner. In terms of inverse models that pair with that, we have sort of 3 families of them. Single dipoles or single equivalent dipoles or equivalent single dipoles, ECD. Distributed source models, which most people will know in here as called minimum norm estimates. If you've ever heard that term, those are distributed source models, and beamforming. I'm going to do my best to talk about the first 2, and I'm going to hand wave at the third and encourage you all to come to the MEG talk that's later in the series, because the MEG core has done a lot of work, just incredible work on beamforming. Okay, so single current dipoles. These are basically equivalent current dipoles. These assume that the EEG signals are generated by kind of one spot in the head. So only one part of the head is going to be active at a time, although even with these, you could say seed multiple seeds at a time. It's just that the dipoles tend to be like discrete and kind of big. You specify the location, just like in the VISA simulator that I showed you before, in X, Y, and Z, and also the orientation and strength. So dipoles project in a direction. It's not just that I have a blob in the head that's kind of going everywhere. This isn't Minecraft. And then, our quality is specified by either like residual variance or goodness of fit metric. And these are really useful for picking up on seizures. They're really good at early components. If you have a N100 and you want to say, is this in visual cortex or auditory cortex? Single dipoles do it almost every time. They're not so great at more complex things, particularly if you have a subject responding at the same time as something that you're trying to measure. And here on the here on the right, you'll see hopefully a movie starting. But yeah, so it kind of bounces in place. So if I just see the dipole there, and then I fit the dipole, you'll see it bounce around like that. So how single dipoles work. Minimum norm, as I mentioned before, sort of the de facto standard in most of what we're doing now. It is well implemented in many, many softwares. Here we're doing a best fit of the sensory data while trying to minimize the overall amplitude of the brain. So unlike single dipole that says I have one source in the brain, minimum norm, what I'm doing is I'm saying all of the brain can be active. It's just all active to a different amount. So some parts of the brain are like super active, other parts are like minimally active. And it's cool because minimum norm actually fits the problem really, really well. Minimum norm gives us pretty good solutions that look very similar to MEG source solutions and to fMRI. The problem is that we know that the brain doesn't work in a minimum norm kind of equation, right? Like not all of your neurons in the brain are active at differing levels at the same time. Neurons are on or off, either or. They're either firing, recovering, or hanging out. Yes, there's probably 3 other states. But what's kind of cool about minimum norm, other than obviously it works and it fits the data, is that they are incredibly computationally efficient. So what used to take us a really long time to do source analysis now takes seconds. They can handle very complex sensor configuration. So not just EEG sensors, not just MEG sensors, but combinations of EEG and MEG sensors. In fact, MEG is particularly cool because you can have magnetometers that can see deep into the head and gradiometers that see very shallow on the head. And you can fit minimum norm solutions that use the combination of those deep sensors and shallow sensors at the same time, or use EEG plus MEG data together. And as I showed last time, as in the talk on Thursday of last week, the combination of EEG and MEG is better than just one alone, and not just because you're adding more sensors, but because you're adding different types of sensors that see different things. So the limitations to M&E, besides we know the brain doesn't really work like this, is that it does tend to produce very spatially smeared results. So shown here in the upper right corner is a N170 to faces versus Chinese characters. And you can see that, sure enough, in faces, we see a nice fusiform face area, and then in characters, we see a language area. Importantly, these were people who were bilingual between English and Mandarin. But M&E also does have a lot of difficulty with deep sources. So it's not perfect, but it is often what people deal with because, as I said, it gives us pretty believable answers. I'm going to give just a brief bit of beamforming. So beamforming is a type of source analysis, but here what we're doing is we're doing source analysis by applying spatial filters to fit the data. And so those spatial filters can pick up on certain brain regions, in particular, being active, that may have different unique frequencies in and of themselves, and that you can tune the beamformer to pick up on certain brain areas if you want to. Some common types of beamforming are well, all of these, but SAM, I believe, was actually developed majorly here at the NIH, and one of the original authors of the SAM pipeline is still here and still working on SAM. So there's a lot to explore on their wiki and also on their GitHub, and also you can email them. They're awesome. Beamforming can obviously handle multiple sources, much like minimum norm solutions. You don't need prior assumptions. You get good spatial resolution, but it can be tricky if you have a lot of very correlated sources. It's really the main con. Okay, I have 10 minutes left, so I'm going to talk a little bit about how to do EEG and EEG-fMRI here at the NIH, in case you're interested. So we have a lot of EEG systems now. I sort of woke up one day and they multiplied like rabbits. We have two 256-channel in-scanner simultaneous EEG-fMRI systems. Both of them were made by EGI. They're both high impedance systems, and they both work with our electrode triangulation wand so that you can localize the sensors on the head. We also have one out-of-scanner G10 neuromodulation system, also made by EGI. They all use the same nets, which is part of why we've been so faithful in buying systems from the same company. So all of these have 256 channels, and you can use the same nets, whether they're MRI or neuromodulation. With the G10 system, you can do alternating current or direct current stimulation. So you can zap people in different ways, or you can even do random noise stimulation. And what's really cool about this is a lot of the old TDCSs literally look like car batteries with two sponges attached to leads, and you just kind of like tap them on people's heads. Did not look fun. I would not have volunteered for those. This is more tame. What's cool here is that in between using your neurostimulation, you can record the EEG. So you can be looking at the EEG, and then you can do neuromodulation stimulation, and then you can record the EEG directly after. So you could do a whole bunch of trials of some particular task, and then you could do neuromodulation for either a couple of seconds or a couple of minutes, and then you could do a number of other trials and see if that neuromodulation actually worked. As I mentioned, the NDI sensor for triangulating electrodes we also have a data storage node, which is kind of like XNAP for your EEG data. It stores your EEG data and any assorted extras, including electrode location files, screen captures. It will even process your data, much like XNAT. So you can go from EEG to ERPs and do some basic source analysis all in the web page application. Here at the NIH, particularly in the Center for Multimodal Neuroimaging, Josh Steves and I wrote the Python package to communicate between PsychoPy and the EGI amplifier for doing millisecond accuracy timing. It's super flexible. You can use it with anything you can do with PsychoPy, and it's 9 lines of code for you, a few hundred lines of code. Works incredibly well. Millisecond accuracy timing, no drift. Once you have sort of your idea for an experiment, make your experiments, tie in with PsychoPy, or we also support E prime, in which case PST made an extension for their application that works quite well. The next step is to learn how to use the system. So we do training on net applications. This video is sped up. No one moves this quickly, although shaky cam has become a thing. I do trainings 1 to 2 times a year, ideal for when new people join your lab. But you also learn how to hook the EEG system into the MRI, proper patient subject care, how to not zap anyone, and also how to get really clean data, because good data is the most important part of this. We have iterated on our methods so much that I'm very proud of the quality of data coming out of our simultaneous EEG-fMRI, which is one of the reasons that a lot of people say they don't do simultaneous, is because data quality is so suspect. Once you've got your data collected, we'll teach you how to analyze it using either Python notebooks, or we have processing nodes with commercial programs, including EGI's own NetStation or Visa. And we also have some tutorials for doing Brainstorm and Field Trip, but also the Brainstorm and Field Trips people were here not that long ago, and I feel like they're overdue to come back and visit. But the main thrust of it is, once you analyze, before you can really analyze your data, you have to do some MR artifact removal. And so we have gradient artifacts shown, original data here on the left, and then artifacts removed here on the right. And essentially, these aren't terribly hard to get rid of. So for removing the gradient artifacts, because it's so consistent, the gradient is happening every, say, 2 seconds, and it's evenly distributed over those 2 seconds, we know what it looks like by just averaging together our EEG data. And so as long as we know what the gradient looks like, we can build a subtraction, and we can subtract out any template we want. Now, what's really cool about MRI is MRI is really good at figuring out if someone moved during your study, right? Like, you get these little like plots and matrices that show you, did they move in the XYZ, roll, pitch, and yaw, any of those. So you can also import these MRI movement files into your EEG data analysis, and then build your template to subtract out the gradients based on only the times that they didn't move. Because obviously, if they moved, your gradient subtraction is not going to be perfect. Here you can get it pretty close to perfect. It's great. And so subduing artifacts really comes down to, we have our original data, we subtract out the MR artifacts, we filter it down just like we would any other kind of EEG data. So shown here in the third pane from, say, 0.1 to 30 hertz. And then we can reduce out the BCG artifact. That's the artifact that's caused by your heart beating inside the scanner, which causes the electrodes on your face and other squishy parts of your head to move ever so slightly in the magnetic field. That causes an artifact. We can model that with a PCA pretty well. We know that it follows the heartbeat by about 200 milliseconds. And so every time you see an EKG R curve, you say, okay, go out 200 milliseconds, run, create a moving average for that time space, decompose it, and then just remove it over the course of your recording. Works incredibly well. Works great in Visa as well, because Visa does this both in a spatial way by saying like where on the head every electrode is, and then you can remove the artifact by counting everything as a dependency around it. And I will say, like, pre-processing makes a difference. So how you remove your artifacts can make a pretty big difference. So shown here on the left and the right are two different pre-processing pipelines of the exact same data on the exact same subject. Which one do you think looks better? Got one vote for the right. The correct answer is the right. Yeah. And these are just subtle changes to which softwares or how we do our pre-processing. And you get all of this. We have all of this in notebooks to provide to. Now, I did get asked last time, or maybe a year ago, about this paper, which is written by the author of EEG Lab, saying that EEG is better left alone, which they make some great arguments for like why you shouldn't do certain kinds of pre-processing things on your EEG data, but removing artifacts, marking bad channels, those are all things everyone agrees you should do in order to have usable data. So once you know how to use the system, analyze your data, you can schedule, just like you schedule an MRI here at NIH. Unlike the MRIs, we don't have pre-allocated time windows. It's on a first come, first served basis, but we have two systems. So we have yet to have any conflicts since we added the second system. And it's pre-wired into most of our 3T scanners. So 3TB, 3TD, and then IEEE Prisma. Anyone who wants it on 3TA, I can do that essentially in a day. And I will leave you with the collect some awesome data. Okay. Yeah, special thanks to the fMRI board that I'm part of. And then, of course, Sean Merritt, my emotional support dog, and my parents, who, for whatever reason, for better or for worse, got me involved in EEG.